Well, hello everyone, and what I want to do in this video for Chem 2100 is to talk a little bit about what I think is a really nice way to think about learning organic chemistry. And in order to be able to give us an example of a molecule that I think is really useful here, I want to start with something, a nice simple molecule shown on the screen here, this molecule Taxol. Okay, I agree, it's not that simple of a molecule, but I think it's a really nice example to illustrate some of the ideas that I'd like to share, get across about how to think about learning molecules. And I say, even though this looks like a sort of confusing mass of atoms and elements and maybe things you haven't seen before, I promise by the end of Organic 1, a lot of this will be a bit more familiar to you as well. I like this molecule because it's what's a so-called natural product. It's produced by the Pacific yew tree as a very effective anti-cancer treatment for head, neck, and breast cancers as well. The problem with this particular molecule is the tree has to be a mature tree, about 100 years old, before it starts producing Taxol. It's got a very low yield, and you need a lot of tree bark to get enough Taxol to make enough for a cancer treatment. So this is where, as I get through this video, I'll show you the power of organic chemistry to address the problem of that limited supply of this particular molecule. And the idea that behind this, and this, I'm not the first one to come up with this idea, is to think of organic chemistry as a second language. And in fact, our textbook author, David Klein, has a series of books with that title where he kind of expands on some of the concepts that shares. So I like to compare it to the idea of learning a language. So for example, if you went to learn the English language, you work with a basic set of building blocks for that language, our 26-letter alphabet shown here. And some of the first things you learn are the order of those basic elements of the language and some of the individual characteristics like their pronunciation as well. And then you can make more complex combinations out of those basic elements. You can start getting simple sentences together, and you can put those sentences in particular combinations that convey an idea or a concept here. And so even with these very simple sentences on this screen, you can picture some basic fundamental ideas from the language. And then English, as it becomes more complicated, can also be to some extent a work of art. And so the line on the screen here is reproduced from a great work of English language literature. And if you're an adept student of that English language, and maybe you've read that work of literature, you can remember a little bit, not only about the work itself, but for example, in this particular point in that story, the struggle the character is going through and sort of the consequential decisions that come out of this particular line being present in that work of art as well. Now, the other thing that you can also do if you're a good student of the English language is that you can look at this particular combination of letters and words, and you can realize that fundamentally they seem kind of similar to the line we just had on the screen, but that there's fundamental rules of English language structure and flow that are violated here, and even fundamentals like spelling that are failed here as well. So that even though this looks on the surface to be similar or okay, there's just things wrong with it as well. Now in chemistry, we've got a different alphabet. It's got considerably more letters than the English language does. Now it's up to about 120 elements in the periodic table. But we think you learned a bit about this in general chemistry, why they're in rows, why they're in groups, and the chemical properties associated with each of those rows and groups as well. In organic chemistry, that alphabet shrinks down a lot for us. We've got carbon, nitrogen, oxygen, and hydrogen that are critical for organic chemistry. We're going to see those elements a lot, and we rely on our understanding of their chemistry and bonding to explain a lot of the things that we see in this course. The elements in green are important for organic chemistry, and we will see them in our course, in Organic 2 and Organic 3 if you stick around for those. We see them an awful lot, and we use them in various functional groups to add some chemical reactivity to our organic molecules. And the ones in blue are useful for organic chemistry. They pop up from time to time. We'll see them a couple of times in Organic 1 and a couple of the other courses that you take as well. Now, the organic words are what we call functional groups, shown on the screen here. You may or may not have seen these from time to time earlier, but alcohols, acids, esters, and things like that, we will see repeatedly. We'll explain them to you more, but these are the fundamental words of organic chemistry, and knowing these patterns explains a lot of chemical reactivity. And then the organic bad words are things like this, where each one of these molecules has something fundamentally wrong with its structure and bonding, and there's some failures of structure here as well. You'll get the chance to explore these a bit more. So what does this have to do with Taxol? Well, Taxol is our organic chemistry work of art. This is this big complex molecule. And what we get to learn here, if we know a little bit about those organic words, those functional groups, is we can predict which is the most acidic proton, what's the best leaving group, which of these functional groups represented in this molecule could react with a nucleophile, for example. And we'll explain those terms and we'll see those concepts right at the end of our time together in Organic 1. And this right here is our Shakespeare. And what we're seeing here on this diagram on the screen is the fact that at the very top is the molecule Taxol, shown in a slightly different representation than what we've had on the screen before. But this is a roadmap that allows us to plan a complete synthetic strategy to make Taxol from very simple starting materials. And each one of these reactions, to some extent, are ones that you'll get the opportunity to see, maybe not with us in Organic 1, but some in Organic 2 and some in Organic 3 for those few of you planning to go on quite that far. But for me, the elegance and beauty of this is that we know how these elements are going to, how these organic functional groups are going to react together, and we can plan out a strategy that takes advantage of their chemical reactivity to take some very simple, easy to obtain molecules and turns it into this incredible chemical complexity like Taxol, and in some part is a way to be able to make enough of that molecule to effectively use it as an anti-cancer treatment as well. And so the basic rules and structure of bonding, which we'll spend a lot of time together on to get in this course, are the things that allow us to understand how complex molecules like Taxol behave and start being able to understand how to do things like make these more complex molecules. And so with that, I'll say that's a kind of a bit of a welcome to Organic 1, and so glad to have you all in the course, and we'll get started with some of the ideas of these concepts and bonding in our very first lecture together.